Hello, everybody. Welcome. We're going to be continuing our study of continuous hyperreal functions. Okay. So this is 1.7 continued. Okay. So we're going to prove the continuity of trigonometric functions. So let's review some trigonometry. Recall that the sine function, sine of x, is an odd function. Geometrically speaking, that's due to the fact that the sine function has anti-symmetry across the y-axis. And that's due to the fact that, let's say this is some x, and up here, over here, this is some sine of x. And then over here, this is negative x. Notice that this right here is your negative sine of x. All right. So that means that sine of negative x is equal to negative sine of x, and that sine of x is equal to sine of x, obviously. But notice that to make sine of negative x be equivalent to sine of x, we use this equation and this equation, and that implies that negative sine of x is the same thing as sine of negative x, meaning that that negative inside the parentheses pops out. That's what it means to be an odd function. A function f of x is odd if f of negative x is equal to negative f of x. And you guys remember that from college algebra. Another piece of information we want to address is the fact that this is the Pythagorean identity. Sine squared x plus cosine squared x is equal to 1. Okay, and notice that if we solve for cosine squared x, we get 1 minus sine squared x. All right. Another one of these identities that is going to be useful in the proofs of the fact that the trigonometric functions are continuous is the sum and difference. Okay, so the sum of sine of some a plus b, where a and b are angles, is the sine of a cosine of b plus cosine of a sine of b. And we derive this in trigonometry if you take trigonometry with me. And then cosine of a plus b is equal to cosine of a cosine of b minus sine of a sine b. And these equations can be derived, but we'll take them as given. And another useful fact is that if the domain ranges between 0 and pi over 2, that implies that this inequality holds. So these facts will be useful when we're proving that the trigonometric functions are continuous. All right. And let's not forget the transfer principle. Okay. So moving on to another sheet of paper. Let's not forget that the transfer principle this gives us that the fact that, like, let's say if we have this, the transfer principle implies that this is true, that the same is true for if we were to plug in a hyperreal number in for x. And of course, negatives All right. But don't forget the fact that the sine function is an odd function allows us to assert this equation. All right. Also, that by the transfer principle that this is true. Okay. And we note that sine squared alpha is basically just an alpha. Okay. And this renders the real result 1. And that makes a lot of sense because the cosine of 0 is 1. And the cosine of 0 squared is just 1 squared, which is 1. And alpha is a number that is infinitesimal. So it's infinitely close to the value 0. So that's why cosine of alpha can render the real result 1. So let's prove that the sine of x is continuous. Here's our theorem. Let's prove that the sine of x is continuous. All right. To do that, we have to take the limit as x approaches, let's say, some arbitrary real number k, sine of x. Notice that this is the same thing as evaluating sine of k plus alpha. Notice that if we look at our sum, sine of a plus b is equal to sine of a cosine of b plus cosine of a sine b, where a is like our k and our b is like our alpha. So we get sine of k cosine of alpha plus cosine of k sine alpha. Okay. But then this is equivalent to sine of k, which is unknown, but cosine of alpha, we know alpha is basically 0. So this approximates to 1 because cosine of 0 is 1. And we get just cosine of k here. Sine of alpha is basically 0 because alpha is basically 0. So this is multiplied times 0. So this whole thing goes to 0, and anything times 1 is itself. So we get that the sine of k plus alpha reduces to sine of k, which, what does this imply? Well, it implies that it's continuous because we showed that the limit as x approaches k of our function, which is equivalent to our function evaluated at k plus alpha, reduces to the function value, just evaluating it at k. That is the definition of being a continuous function, is that if the limit as x approaches that value is the same as evaluating the function at that value. So we're done. We have shown that the sine function is continuous. Okay. Let's also add to this theorem that the cosine, let's prove that cosine is a continuous function. Let's take the limit as x approaches k, cosine of x. All right. This is the same thing as the cosine of x plus some alpha. Did I say x? I meant k. K plus some alpha. Notice that by the sum formula, cosine of a plus b is equal to cosine of a cosine of b minus sine a sine b. So this becomes cosine of k cosine of alpha minus sine k sine alpha. All right, we notice that the cosine of alpha evaluates to a 1 because alpha is basically 0 and cosine of 0 is 1. And that the sine of alpha basically goes to 0 because sine of 0 is 0. So then we end up getting that this whole thing goes to 0, and this reduces to just cosine of k, which again shows that the limit as x approaches k of cosine of x is equal to the evaluating cosine at k. So we've shown that it's continuous. All right. It can easily be verified that due to the fact that tangent of x is merely the ratio of sine of x over cosine of x, that the tangent of x is also a continuous function. However, we must note that if cosine of x is in the denominator, we must omit the values of x such that when we input them into our function, that they don't output 0, because then we'd be dividing by 0. So again, to find that domain, we want cosine of x to never equal 0. So that means when we take the cosine inverse of both sides, that means we get x cannot equal the cosine inverse of 0. The cosine inverse of 0, as you remember from trigonometry, is a question. It says, for what angles does the cosine equal 0? Okay, well, we know that pi over 2, the cosine of pi over 2 is 0 because it's at 90 degrees. And so that's definitely an angle. Furthermore, another one is 3 pi over 2, which is the analog of 270 degrees. Okay. Why did I separate these? Well, that's due to the fact that those aren't the only ones. Matter of fact, there's an infinite number of values of x such that the cosine inverse of 0 is that angle. So what we have to do is say pi over 2 and 3 pi over 2, we have to add a plus or minus 2n pi, plus or minus 2n pi, where n is an element of the integers, and that's due to the fact that the period of the cosine function is 2 pi, and adding or subtracting any integer multiple of 2 pi will land you in the same spot. Therefore, we have to take those values into account. So tangent of x will have the specific domain in which it will avoid all the values that we've highlighted here. So the domain is everything except these values. All right. So on your test and on your homework, make sure that you explicitly highlight these facts. You cannot assume that the tangent of x is a continuous function for all real numbers, because it is clearly not defined for all real inputs. Okay, but when we avoid these values in this box, the tangent function is defined, and therefore it is continuous because it's a ratio of continuous functions. That can be proved as well. Okay, but let's prove that the composition of continuous functions is a continuous function. So here's a theorem. For functions f and g, f composed with g of x is continuous if f and g are continuous. So basically, let's assume f and g are continuous real valued functions. All right. What does that buy us? Well, that means the limit as x approaches k of f of x is equal to f of k, and that the limit as x approaches k of g of x is equal to g of k. All right, that's going to come in handy. We want to show that the composition of these two functions is continuous. So we have to show that this limit ends up equaling the function evaluated at k. Notice that by definition, this is equal to the limit as x approaches k of f of g of x. All right. But then we can take that limit away and say this is the same thing as f of g of k plus some arbitrary infinitesimal value alpha. But we know g is continuous, which implies that we may assert that this is true, that this equation holds. Okay? But notice that by definition of composition of functions, this is the same thing as this. notice that we have proved that f composed with g of x is a continuous function, because the limit as x approaches k of f composed with g of x is equal to f composed with g of x evaluated at k. So we're done. Therefore, I put a box, and we could write a QED for quod erat demonstratum. Now, we're done with section 1.7. We're on to section 1.8. And this is the last section before our first exam. All right. So recall when we tried to find the slope of the tangent line to this function before, a long time ago in our beginning discussions of calculus, we wanted to find what is the slope of the tangent line at x equals 1 of this function. What is this function? Well, when we graph it, notice it's a quadratic function, has an x squared in it, but it's a minus. So that means it's a parabola that opens down. And that 4 gives it a vertical shift of 1, 2, 3, 4, and it opens down like so. All right. We can figure out what these points are that touch the x-axis by saying, okay, at this point, the y value is 0. So that means 0 is equal to 4 minus x squared. Add x squared. This is equal to 4. That implies that x is equal to plus or minus the square root of 4. That implies x is equal to plus or minus 2. So this is at negative 2 comma 0 and at positive 2 comma 0. All right. Now, we want to know that at x equals 1, what is the slope of the tangent line? Like so. And I'll draw the tangent line in red. Okay. I'll call this t of x, which is equal to some mx plus b. And this point is at 1 comma f of 1. Notice that f of 1 is plugging 1 into the function. Okay. So we aspire to find out what this tangent line is. And I have t of x is equal to mx plus b, but really what we want to know is just the slope. Right now, we're just interested in what is m. So then we think of the definition of slope. We think of what is slope defined as. Slope is m, which is equal to y2 minus y1 over x2 minus x1, where we have a pair of points x1, y1, and x2, y2. Okay. Recall that we tried to solve this problem by saying, well, take x1 and y1 to be 1, 3, and x2 and y2 to be 1, 3. But then this equation gives you 0 over 0, which is undefined. So that idea didn't work. Then we tried another idea where we said, okay, let x1, y1 be 1, 3, but let x2, y2 be some other point, maybe over here, at 2, 0. But then when you do that, you don't get the slope of the tangent line, okay? You get the slope. Let me get a pen here. You get the slope of a secant line, which is not the same. Call that s of x. That's the slope of the secant line. That's not the slope of the tangent line. The tangent line only touches the curve for minus x squared at 1 point. The secant line touches the curve at 2 points, even though it looks like it's touching it at more than 2 points. If I drew it perfectly, it would only touch it at 2 points. But even so, this is bad and this is bad. So this is bad because we're dividing by 0. This is bad because this is not really what we want at all. So we were stuck a long time ago. We were stuck. But the hyperreal numbers allows us to be unstuck. Recall that the point of inventing calculus was that we could basically divide by almost zero and get away with it. Okay? So let's try and solve this problem once and for all. Let x1, y1 be that 1, 3. Let x2, y2 be 1 plus alpha, f of 1 plus alpha. Just scoot over by an infinitely small value, okay? So f of 1 plus alpha is really 4 minus the quantity 1 plus alpha squared, which is 4 minus the quantity 1 plus 2 alpha plus alpha squared. When you distribute the negative, you get 4 minus 1 minus 2 alpha minus alpha squared, which is equal to a 3 minus 2 alpha minus alpha squared. This is your f of 1 plus alpha. So x2 comma y2 ends up equaling 1 plus alpha comma 3 minus 2 alpha minus alpha squared. All right, so our slope m, which is equal to y2 minus y1, or x2 minus x1, we can now actually calculate this slope. Y2 is 3 minus 2 alpha minus alpha squared, minus our y1, which was 3, all over x2, which is 1 plus alpha, minus our x1, which was 1. Notice that these cancel. So we get a negative alpha squared minus 2 alpha all over alpha. We can factor out alpha over here. So we get negative alpha minus 2 all over alpha. Cancel out alpha. You get a negative alpha minus 2, which renders the real result minus 2. My goodness. Wow. What you guys need to realize is this is incredible. The invention of calculus, which boils down to the invention of thinking of infinitely small numbers and how to use them to get around this problem, allowed us to extract this number -2. It allowed us to excavate this piece of truth that was inaccessible to our minds prior to the invention of the hyperreal numbers. That is a big deal. This was a revolutionary discovery. This discovery led to the invention of Newtonian mechanics, which led to the invention of classical physics, which led to the invention of the Industrial Revolution, where machines, technology, trains, engines, factories, it was basically the theoretical framework that allowed human beings to exit the Dark Ages and enter the Industrial Age. So this is the theoretical framework behind physics, at least for Newtonian physics. This was an incredible achievement of the human mind. So I can't overstate how important the fact that we were able to extract this information -2 is. So moving on, we can actually find the tangent line t of x is equal to mx plus b. Notice that we know m, that's equal to -x plus b. This is our t of x. But notice that just putting it into slope-intercept form doesn't give us the equation for the tangent line. We can use slope-intercept form. We can use a point slope. The point slope form, y minus y1 is equal to m times x minus x1. Given a slope and a point, x1, y1, and a m, we can create the equation of a line with this equation. And we know both those values. This is a 1 and a 3. And now we've extracted the fact that this equals a -2. So y minus 3 is equal to -2 times x minus 1. This equals -2x plus 2. That implies we get y minus 3 is equal to -2x plus 2. That implies that y is equal to -2x plus a 5. And, you know, we can call that our t of x. That's precisely the tangent line. So now we know that is the equation of the tangent line, and we found the slope as well. So we will see in this section why this is such a big deal. Because right now, it just seems like it's just a trick to get us to finding this value. But you'll realize that this really revolutionized how mathematics can be applied, not only just purely to the subject of math, but also to real life situations. Okay, so notice that we can generalize this fact to any function. Let's say we got some f of x. Let's say we got x is equal to k, all right, for any k real number, okay? Notice that our x1, y1 can be some k f of k, and our x2, y2 can be some k plus alpha f of k plus alpha. And so when we find the slope, m is equal to y2 minus y1 all over x2 minus x1, we get f of k plus alpha minus f of k all over k plus alpha minus k. Okay, these k's cancel. So this reduces to f of k plus alpha minus f of k all over alpha is equal to our slope, m, in general, for any function. What does that look like to you? What does that remind you of? And you hopefully should be able to see it. I need to be mindful of having this on the screen. Just think about what that equation looks like and if it's familiar to you at all. It should be familiar to you. This is equal to the slope of the tangent line to the function. This numerical quantity that outputs m is the slope of the tangent line of the function f of x, precisely at this point, k f of k. And k is any number, so we can actually discover what is the slope of the tangent line of a function at any value that we want. All right, so let's apply this. Let's just apply this knowledge. Let's say we have some function f of x is equal to x squared, and we want to know what is the slope of tangent line at x equals 3. Okay, so m is going to be equal to f of k plus alpha minus f of k all over alpha is the same thing as k plus alpha squared minus k squared all over alpha. This is equal to k squared plus 2k alpha plus alpha squared minus k squared all over alpha. Cancel out the k squareds. And then when we can factor out alpha, we get alpha times the quantity alpha plus 2k all over alpha. Cancel out some alphas and we get alpha plus 2k. This renders the real result 2k. But notice that k is equal to 3. So if you want to actually know the real value, you might want to do this. I was keeping it very general there. We could have replaced k with 3 up here. Okay? We could have just wrote a 3 every time we saw a k. So this would have been, 9 minus a 9, 3. You get the point. So again, it would have reduced down here to 2 times 3, which would have been the same thing as 6. Mathematicians like to work in general. Okay, So now that we found the slope, what is the tangent line? Well, y minus y1 is equal to m times x minus x1 is your best friend. All right. We will utilize the point that we have the function 3 and f of 3, which is 3, 9. When we plug in 3 into this function and you square it, it becomes a 9. So it's at that point we have the slope 6. So we're going to use those values, y minus y1, which is a 9, is equal to 6 times x minus x1, which is a 3. So this becomes 6x minus 18. That implies we get y minus 9 is equal to 6x minus 18. That implies we got y is equal to 6x minus a 9. This is the equation of the tangent line. Okay. Here's a way to check. If this is indeed the tangent line, y of x, then inputting the value 3 should output the same value as what you would evaluate the function at. So y of 3 better equal 9. So let's see. That's 6 times 3 minus 9. That's 18 minus 9, and that's 9. Chink. So that makes a lot of sense. So that's really good. Here's another example. Same function, f of x is equal to x squared. But what about x equals negative 1? Well, you can do this process again. M is equal to f of negative 1 plus alpha minus f of negative 1 all over alpha. That's equal to negative 1 plus alpha quantity squared minus negative 1 squared all over alpha. This equals 1 minus 2 alpha plus alpha squared minus a 1 all over alpha. Cancel out the 1s. We get a factoring out of alpha. We get alpha times the quantity alpha minus 2 divided by alpha. Cancel out the alphas. We get alpha minus 2. This renders the real result negative 2. And this is our slope, m. Okay. Notice, if we knew that this was the equation for the slope of the tangent line, okay, we could create a new slope of a tangent line here, okay? The new slope of the tangent line at this new point, x equals 1, is going to be different. So y minus y1 is equal to m times x minus x1. That would imply, what's a point? Well, negative 1 and f of negative 1, negative 1 and 1, is a point on the curve. So we got y minus y1 times slope times x minus x1. So this becomes a negative 2 times the quantity x plus 1. This becomes a negative 2x minus 2 is equal to our y minus 1. That implies y is equal to negative 2 minus 1. And this has an x on it. Okay. So this is our new equation for the tangent line. And check this out. Y of, here's our check. Y of negative 1 should output a 1. Chink, that works. Okay. Moving on here. Let's see how we're doing on time. Okay, I'm going to pause and do the rest of the video in another video so that I don't run over my time limit here. Okay.